In this section, we're going to discuss identity on the blockchain. Let's start by understanding why we even need to have an identity on the blockchain. Centralized systems can be coerced by other forms of authority to shut down their network. Let's take Napster, for example. Napster had a decentralized network architecture, but they maintained a centralized authority. Therefore, the central authority could be attacked, and by taking out the central authority, could effectively control Napster. This is because Napster relied on that mix of centralized control over a decentralized network. This impacted identity because you need an identity to control. Torrents, on the other hand, they do not operate in the same fashion. Torrents provide a decentralized network with decentralized authority. This allows the nodes to manage identity differently. It's also the reason why torrents are still being used today in spite of the entertainment industry's best efforts to stop it. Torrents remove the central authority. So this begs the question, why didn't point-to-point networks like torrents attain the same level of acclaim as blockchain? Because there's no guarantee that the nodes would do the right thing. Nobody could guarantee that the nodes would cooperate with each other. This leads to an extremely important question. How do you incentivize the nodes on the network to follow the rules? In a torrent system, anyone can download and share a file, but there's not a real incentive to be a good actor on the network. What happens when people do something dishonorable? On a torrent, for instance, and stop seeding the files that ate up bandwidth or occupied space on their computers. Instead of music going through the network or other files, what if it were money going through a point-to-point network, through a bank network, let's say? Your transactions would never be processed reliably. You couldn't trust that the processing was not messed up or either deliberately or accidentally. Further, because of anonymity and the way that identity works on the blockchain, you wouldn't have a way to punish or reward the actors. Blockchain solved this problem. It perfectly incentivized how to create a decentralized, self-contained network using crypto economics. This differed from earlier point-to-point networks because it offered economic incentives to the nodes that followed the rules. Nodes are given money for following the rules. This money is in the form of cryptocurrency. The nodes were punished for tampering with the system, or with past transactions, or submitting a bad transaction. This is why all public blockchains can operate without an authority. It is also the reason why cryptocurrency is mandatory for a public blockchain and not needed for a private blockchain, because you need a way to incentivize the actors on the network. Consider how these rewards and these punishments work, and how a system without a central authority can determine what is valid and what is invalid. On the blockchain, identity is important. You have to be able to prove that your assets actually belong to you. Different blockchains, they use different systems for tracking identity and identity information, but most are based on the principles of public key cryptography. Before we get into the details of how identity works on the blockchain, we need to discuss the basics of public key cryptography. The security of a public key cryptography, it's based on, let's call them hard math problems. So by that I mean a hard math problem is one where it's easy for someone to calculate it, but it's hard for someone to reverse that calculation. Take multiplication, for example. All things considered, multiplication is easy. If you have a little bit of time, something to write with, you can pretty much multiply any two numbers and get the right answer. A computer can do that even more quickly. Factoring, on the other hand, it's hard. The best way to factor a large number is to try every possible factor until you find the right one. While this approach works well if the number to be factored is small, it quickly becomes virtually impossible with a sufficiently large factor. Some public key cryptography algorithms are designed so that breaking the algorithm requires factoring very large, usually prime numbers. Another hard math problem used in public key cryptography is based on exponents and logarithms. Exponents are easy, since it's essentially multiplication, and logarithms are hard, since you're essentially factoring. Most public key algorithms that use exponents use a type called modular exponents. All this means that when they're done calculating the exponent, they divide the result by a publicly known value called the modulus, and they keep only the remainder. RSA is a commonly known public key cryptography algorithm. It's based on exponents and logarithms. RSA uses the power law of exponents. What this means is that if you take a number, you raise that number to a power, and then raise the result to another power, that you'll get the same result as if you simply multiplied the two exponents together and then raise the base to the result. An RSA user chooses two exponents so that any number raised to the product of the two exponents in a given modulus produces the original number. One of these is called the public key, and that public key is distributed freely, while the other is the private key, which is intended to be kept secret. If someone wants to send a private message to the user, they convert it to an integer using a publicly known method. They raise it to the power of the user's public exponent, and they send the result to the user. The user raises the received value to their private exponent, producing the original message. RSA is secure because an attacker must be able to calculate a logarithm to determine the secret message. Since this takes guessing every possible value until the correct one is found, RSA is designed to make the number of potential values so large that finding the right one is pretty close to impossible. Another public key algorithm uses different math behind the scenes, but the basics are effectively the same. A user creates a public key and the private key that can be used together for either encryption or signing, which we'll talk about later. The algorithms are designed so that an authorized user only has to do the, quote, easy calculations, while an attacker has to perform the hard calculations, and the algorithm is designed to make attacking so that the hard algorithms are close to impossible. Public key cryptography is how identity is handled on the blockchain. A user's address on the blockchain, it's their public key. This has several useful properties. Users do not need to reveal their identity on the blockchain, but they can positively identify themselves, since determining their private keys requires solving a, quote, hard problem. Anyone can send a user an encrypted message, since they have easy access to their public key. Users can verify the validity of their transactions using digital signatures. You can think of a digital signature as the opposite of an encrypted message. In RSA, anyone can send an encrypted message to a user by converting it to a number, raising it to their public exponent, and sending the result to them. The user's public and private keys are designed so that the users can retrieve the original message by raising the received message to their private exponent. RSA digital signatures involve the opposite process. A user writes a message and raises a condensed form of the message to the power of their private exponent to create a signature. Then they publish that signature. Their public key and their message are both published together. Anyone can verify the signature using a simple three-step process, condense the attached message using the same method as the message writer, the message originator, raising that attached signature to the user's public key, and verifying that the results of the previous two steps are identical. Digital signatures work for the same reason that encryption works in RSA. An attacker needs to know the user's private key to perform either operation, and the algorithm is designed to make that process difficult or very close to impossible. This means that identity on the blockchain boils down to the possession of a user's private key. So it is absolutely important that that private key be kept safe. In Ethereum, a user's identity is managed using a public key or address, and the user can use the corresponding private key to sign transactions and read encrypted messages that are sent to them. In Hyperledger and Corda, identity is encoded in X509 certificates, which include the user's public key. In Corda specifically, certificates can either be public, which means that they are published to the blockchain, or confidential, meaning that they are only shared with the parties that the owner performs transactions with.